Good morning, everybody. Welcome to this webinar, April 6th, 2016, and we are going to talk about the effects of common cause on the average probability of failure on demand. Well, that may by itself not be that interesting, but as some of you may have experienced in the past, every now and then, when you increase your beta factor or your common cause factor, PFDavg actually goes down, which is completely counterintuitive. So we're going to explore that. We're going to see why that is happening, and we're also going to see why in some cases it may not happen. But we'll talk about how it happens, and in the end we'll see when we are talking about Excellencia, for example, how common cause factor impacts our probability failure on demand calculation. So good morning, good afternoon, whatever time zone you're in. My name is Iwan van Buren, and I am Director of Development at Excellencia. I support both end users and manufacturers, as well as our certification activities, 61511, ISA 84, and 61508 related work. And then I'm responsible for the development, maintenance, certification of the Excellencia software, our SILSTAT software, as well as our CyberFax product that we're using for cyber risk analysis. I'm a member of the ISA 84 committee. For those of you attending the committee meeting at the end of the month, it looks like I'm going to be able to attend that one. And as I said, there's a wide variety of activities that I do within Excellencia. 61508 development support, 61511 assessments support, SIL selection, SIL verification, and then I teach some Excellencia and Excellencia training courses, as well as some of the ISA courses. So today, there's a couple of things that I like to talk about. And first off, when we talk about common cause, every now and then we may run into a counterintuitive observation. In other words, probability of failure on demand goes down when beta is increasing. And in our support desk at the Excellencia team, we get quite a number of questions about that, at least relatively speaking, quite a number of questions on that where users are experiencing this and they're like, hey, wait a minute, that's not what I expected. Of course, as soon as we explain why, then everything is settled, but it made sense to talk about that in a little bit more wider format and have some slides to show with it. So that's an observation that we've seen, and so let's get started and see what is common cause. What are common cause failures and how does it impact our probability of failure on demand, and impact of common cause, and I'll talk about that from a simplified equation perspective. And we will be able to see that PFD may go down if beta increases, but we need to understand common cause in a complete system modeling context, because in cases where PFD may go down as a result of beta increasing, other aspects of the system may actually get hurt by the common cause factor. And eventually we'll look at common cause and Excellencia. So first, that counterintuitive observation. The common concept of common cause is that it's harmful for redundant configuration. It will make redundant units fail at the same time due to a single stress. So the overall expectation is that if common cause increases, your redundant configuration decreases to a 1/1 of non-redundant configuration, which is typically worse for your average probability of failure on demand. So typically we expect increasing common cause will have a negative impact on PFDavg. In some cases it's the other way around. So that kind of suggests that a configuration is safer if there's less redundancy, and that doesn't sound right, correct? Well, let's look at it. So what is common cause? Well, typically, typical definition, the simultaneous or near simultaneous failure of two or more redundant units due to a single stress, or if we look a little bit more formal in IEC 61508, Part 4, 2010 edition, Clause 3.6.10, the failure that is the result of one or more events causing concurrent failures of two or more separate channels in a multiple channel system leading to failure. So we have a single stress, could be multiple events all combined into a single stress event that lead to multiple failures at the same time, and basically defeating the entire system at that point. All right, so let's look at that graphically. On the top left, I have this little picture here where I have an overview of all the failures of a channel, channel 1, and all the failures of a second channel, channel 2, and and there is a certain overlap, and that overlap is an area where both of those channels will fail at the same time due to a single stress. So that's a way to represent how common cause fits within a dual channel system. Another way to look at it is, if we look at the bottom right, we just consider stress distribution, we consider a strength distribution, and for a given scenario we have two stresses. We have two strengths for a dual redundant system, strength 1 and strength 2, and then we have a common cause stress that is simply greater than the two individual strengths. And when that happens, both units will fail at the same time. All right, so how do we model common cause? Well, there are several methods to model common cause. There's a mesh model, there's some other models. Typically in the process industry, or 61508 as an umbrella standard, the typical model that people are looking for when it comes to modeling common cause is the beta model, where beta is the fraction of the failure rate where two or more failures will occur due to same common stress. Now, this is a fraction of a failure rate. That doesn't mean, and we'll see that on the next slide, that there's additional failures that are common cause failures. No, these are typical failures that are part of a product. If you use that product in a non-redundant configuration, single configuration, those failures will occur. But if there's redundancy, multiple failures will occur at multiple units will fail at the same time due to that single stress. So that's a way to look at it. Beta is the fraction of the failure rate where two or more failures will occur due to the same common stress. That beta model allows us to divide a failure rate into two groups of failures: normal, or sometimes referred to as independent failures, failures of a component that are not susceptible to common cause, and common cause failures, which are failures of that component that are susceptible to common cause. And from a formula perspective, beta is the common cause failure rate divided by the total failure rate, or in other words, once we know the total failure rate of a product and we know what beta value to use, and I'll talk about what different beta values we could use, we can calculate the common cause failure rate and the normal failure rate. The sum of the common cause failure rate and the normal failure rate is the total failure rate. So that's the point I tried to make earlier. We don't add more failures to a product's failure rate to account for common cause. No, it's simply a portion of the already existing failures that could occur that will happen simultaneously in multiple units if there's redundancy. So, all right, so we're using this beta model. What's the impact of common cause? And let's look at that from a simplified equation perspective. To start, I put in a slide with the simplified equations. So for a 1 out of 1, it's a dangerous failure rate times a test interval divided by 2 for PFDavg. For 1 out of 2, it's a dangerous failure rate times the test interval squared divided by 3. 2 out of 2, dangerous failure rate times test interval. 2 out of 3, dangerous failure rate times test interval squared. Now keep in mind these are simplified equations. They ignore some critical variables, and we're not even talking about diagnostics. We're not talking about a proof test coverage. We're not talking about site safety index, anything like that. These are very simple formulas that we'll be using to demonstrate the impact of common cause. So if we look at the common cause, and let's start with a 1 out of 2 configuration, because 1 out of 2, that's behaving like we expect it to be. So the typical example will be 2 valves in series where the valves need to close on trip. So if there's a dangerous situation, the valves need to close, and you have the 2 in series. So 1 of the 2 being successful will achieve the safe state. And let's assume we just have a simple safe failure rate and a dangerous failure rate. So we're not talking about diagnostics or anything. You could say everything is undetectable. For simple discussion, simplified discussion, just simply a safe failure rate and a dangerous failure rate. When we calculate the probability of failure on demand, our equation that we will use to calculate that probability of failure on demand is going to consist of 2 separate terms. There's going to be a redundant system term and a common cause system term, or in other words, a term in the PFDavg calculation that will represent, let me get my highlighter here, that will represent, it doesn't like it, all right, that will represent the system behaving as a truly redundant system, and a term of the equation that represents the system behaving as a non-redundant or 1 out of 1 or single system. So those 2 terms, very straightforward. We can, in this case, because it's a 1 out of 2 system, the redundant term is going to be a 1 out of 2. The common cause, the part of the system that does not behave like it's a truly redundant system, that's just going to be a single or non-redundant system, 1 out of 1. And we can look at the overall equation, and we see that 1 out of 2 term, lambda d times ti squared divided by 3. That's the equation that we saw on the previous slide. Let's just go back to that previous slide. Lambda d ti squared divided by 3. And then the second term is the dangerous common cause failure rate times the test interval divided by 2. So one of the things to note here is that the failure rates that we're using are not the standard dangerous failure rate. It's a dangerous normal failure rate for everything that behaves as a normal or independent system, and a dangerous common cause failure rate for everything that behaves as a single or non-redundant system. And how do we get those failure rates? Well, that's something that we already saw earlier. It's the common cause failure rate is beta times the dangerous failure rate in this case, and the dangerous normal is 1 minus beta times the dangerous failure rate. So those 2 formulas are here on the right. So that is the typical equation to calculate a 1 out of 2 configuration PFDavg. So let's plot that. And in this case, I plot it as a function of test interval. So we can see what PFDavg does as a function of test interval. And I assumed a dangerous failure rate of 0.02 failures per year. And I plotted this for 4 different scenarios. A beta factor of 0%, 2%, 5%, and 10%. And what we can see for a given test interval frequency here, so let's say it's 2 years, what we can see is that the probability of failure on demand for the 0% scenario, 0% common cause, everything behaves like a truly redundant system, has the lowest average probability of failure on demand, whereas for a 10% scenario, the highest probability, the highest common cause factor in my example here, we have the highest average probability of failure on demand. So as the common cause factor increases, PFDavg increases. Well, that's exactly as we expect. That's exactly what we expect, because common cause is usually detrimental to a redundant configuration. All right, so that's a 1 out of 2. Behaves exactly as we expect. Now let's look at a 2 out of 2 configuration, or a configuration where, in this example, there are 2 valves in parallel, and they need to close and trip. So if there's a dangerous condition in the process, the valves need to go to the energized state or closed state. And in order for flow to stop in this particular scenario, both valves will need to close. Therefore, it's a 2 out of 2. Same safe and dangerous failure rate. Let's calculate the average probability of failure on demand. And we did a little bit more here with the equations, but the start is exactly the same. There's a redundant portion of the formula and a common cause portion of the formula. It's exactly the same as what we did for a 1 out of 2. The redundant portion, in this case, is going to be the 2 out of 2 portion. After all, we're using a 2 out of 2 voting architecture here. The common cause portion remains the same. It's the 1 out of 1 or non-redundant configuration. Substituting those, substituting the correct formulas for these two terms, so lambda d times t and lambda d normal and lambda d common cause times ti divided by 2. Now, where do these formulas come from? They come from that simplified equation, lambda d times t and the non-redundant lambda d times t divided by 2. All right. We have the definition of a common cause failure rate and a normal failure rate. Lambda d common cause, beta times the dangerous failure rate, lambda dangerous normal, 1 minus beta times the dangerous failure rate. And we can substitute those in the formula, and we get 1 minus beta times lambda d, which is lambda dn. So this equates to, over here, times ti, plus beta times the dangerous failure rate, this portion, which equates to the dangerous common cause failure rate, times ti divided by 2. Well, if we have that, we can then see that there's an area of the formula that is the same, lambda d times ti. And here it's multiplied by 1 minus beta, and here it's multiplied, so here it's 1 minus beta times lambda dti. Here it's beta divided by 2 times lambda dti, and we can rearrange that equation and make it 1 minus beta plus beta divided by 2 times lambda d multiplied with ti. And then if we substitute, or if we solve that, what we see is that for an average probability of failure on demand for a 2 out of 2 configuration, the equation is 1 minus beta divided by 2 multiplied with the dangerous failure rate multiplied with the test interval. All right, I have a question. I forgot to mention that earlier, but if you have a question, you can type it on the right-hand side. All right, so I got a question here, is why are you including beta in the 2 out of 2 logic? Well, I'm using the exact same logic, exact same formula that I did for a 1 out of 2 system. I'm using the exact same approach that I did for 1 out of 2, and we all agreed that for 1 out of 2 this is the correct approach. So the only thing that's different now is I'm putting in a redundant system. And I hear what you're, the question here is, why did you include beta in the 2 out of 2 system? Well, so far, and the second part of the argument is, well, if I lose one valve, I lose my safety function. It's absolutely true. You lose one valve, you lose your safety function. And if you just look at PFDavg, you may say, you know what, that doesn't make sense to consider common cause, because anything fails, I will immediately fail. But anything that I've done so far is I've used the exact same approach for a 2 out of 2 configuration that I've done for a 1 out of 2 configuration. And for a 1 out of 2 configuration, we agree. So if I would do the same approach for a 2 out of 3 configuration, we would probably argue, hey, you need to do the same thing. Or for a 3 out of 4 configuration, we need to do the same thing, redundant system plus common cause. But if we have a M out of M, or X out of X, whatever you want to call it, 2 out of 2, 3 out of 3, 4 out of 4, it sounds a little counterintuitive to account for common cause. And there may be a point there, but as we will see in the next section of the slides, if you look at more than just probability of failure, you will see that common cause does have an impact on these M out of M redundant configurations. All right, so if I plot that equation with the beta factors and the failure rate that I assumed here, not that big of an impact overall, but we can see, and I zoomed in here on the right-hand side just so we could see it a little bit better. We can see that if beta increases, the average probability of failure on the month will decrease. If the 2 out of 2 system behaves more like a single system, its probability of failure will decrease. And that's what we typically don't expect. We don't expect that if beta increases, we don't expect that if common cause increases, that PFDavg decreases. But here's an example as to why that may happen for a 2 out of 2 configuration. Now again, I use a very simplified equation. There's many more parameters that we should take into consideration in our average probability of failure on demand calculation. But using just a simple approach that everybody agrees on for a 1 out of 2 configuration, and using the same approach for a 2 out of 2 configuration, we have an explanation as to why the average probability of failure in the month decreases. So that may sound still a little counterintuitive. Why do you account for common cause in a system where a single failure will immediately cause that entire system to fail? Well, one of the things that that you need to look at when you talk about common cause and you talk about redundancy is a little bit further than just probability of failure on demand. Absolutely, it's a very important parameter, and the standards talk about pretty much just probability of failure on demand. But there is more when we model a complete system. So let's look at another aspect of safety systems. Every now and then they will fail spuriously. They will transition to the safe state even though there is no demand from the process. So let's look at a 2 out of 2 configuration and look at the spurious strip. We can use the same simplified equations. Let me go a couple of slides back. And here we have the equations for the spurious strip as well. And what we will see when we look at a 2 out of 2 configuration, which is designed to protect against spurious failures, a single valve failing spurious does not shut down the process. Both valves will need to fail spurious. And we look at the spurious strip rate in that case, we see the same behavior that we saw in the previous example when we just talk about probability of failure demand. There's a redundant portion in the equation and there's a common cause portion in the equation. But here we see that a certain term squared, which is but an indication that multiple units need to fail safe before you lose the before your entire configuration fails safe. Added to that term is a safe common cause failure rate, which is the non-redundant single 1 out of 1 spurious strip rate for a simplified equation example. And what we would see, and I didn't plot these, but what we would see in this case is that for that spurious strip rate, that common cause factor will negatively impact the spurious strip rate. Spurious strip rate will actually go up with common cause going up. And then it starts to make sense, because what we're seeing now is that common cause does have a negative impact, but it has a negative impact on the parameter that the configuration was designed to prevent. If we look at a 1 out of 2 configuration, and we do the same approach, redundant 1 out of 2, common cause 1 out of 1, we apply the beta factor on the spurious strip rate, we have 2 times the safe failure rate normal, though that is the spurious strip rate for a 1 out of 2 configuration, and we add to that the spurious strip rate common cause. We see that we can simplify that equation. We can see that that evolves to 2 minus beta times the safe failure rate. So as beta increases, the spurious strip rate will go down. It's the same behavior that we saw for probability of failure on demand for a 2 out of 2 configuration. It's the same behavior that we see here for spurious strip and a 1 out of 2. Why is that? Well, a 1 out of 2 configuration is intended to increase safety at the cost of spurious failures. But the more that 1 out of 2 configuration will start to behave as 1, the less likely the spurious strip, the less likely it is that there will be a spurious strip. So the same behavior we see for PFDavg for 2 out of 2 is what we see for spurious strip rate in 1 out of 1. 1 out of 2. Now we can model that complete system, and again, these are simplified models. You know, there's no repair actions, no tests, there's no, there's no diagnostics. This is just 2 failure mode models. But one of the things that we see when we look at a complete system model is that yes, there's a transition from the OK state directly into the fail dangerous state, and that's a dangerous common cause factor. So 1 out of 2 intended to increase safety, reduce probability of failure on demand, typically at the cost of increasing spurious failures. We'll see a direct transition to the dangerous or fail dangerous state from the OK state due to common cause. We have a regular failure or the normal failure. Since we have 2 units, 2 times the dangerous normal failure, go to a state where 1 of the 2 fails dangerous, and I'm still operational. I would still be successful. I'll still be able to prevent a dangerous situation with the second one. And then, from that intermediate state, there is just a simple transition to if the remaining valve fails safe, you shut down. If the second valve fails dangerous, you fail dangerous. At the same time, we see a transition from the OK state to the fail safe, either valve failing safe or a common cause failure. So when you do complete system model, you see both aspects of common cause, probability of failure, and spurious strip rate, and including common cause in the spurious strip makes sense if you include it in the dangerous failure aspect. Now the same approach is true for a 2 out of 2 system. We have 2 out of 2 designed to prevent spurious failures. We see that if a safe common cause failure occurs, we immediately transition to the fail-safe state through the safe common cause failure rate. We see that we can have a scenario where 1 of the 2 fails safe. We would still be able to continue to operate. 1 of them is closed. We only need to close the second one. So a second safe failure will bring us to the safe state. But a dangerous failure at that point will lead us to fail dangerous, because at that point we can no longer go to the safe state if 1 of the 2 fails dangerous. So that makes sense. From the OK state, there's also the transition of a dangerous failure directly to the fail dangerous state, as one of the attendees just remarked. Any dangerous failure, I immediately fail dangerous. Absolutely right. But there's also the common cause factor, and we've seen that that may actually impact the probability of failure on demand for the common cause. So in this case, it's the opposite of the 1 out of 2. Makes perfect sense to consider a common cause in a configuration that is designed to protect against spurious failures, and it may sound a little counterintuitive to include it, but from a complete system model, it makes sense again. So how does this look in Excellencia? Obviously, we've accounted for common cause in Excellencia, and there's a couple of areas where we do have common cause in the tool. Whenever you have redundancy, so for example, one of the two, you will be able to specify a beta factor. Also, if you have multiple groups, you will be able to specify a beta factor for voting between groups. So there's multiple ways that you can account for common cause in Excellencia. And let's just have a look at that. And I prepared a simple project where we have I have two SIFs. One is a 1 out of 2, one is a 2 out of 2. And in this case, let's ignore the parameters at the top. Let's ignore the navigation portion. We just want to look at the transmitter area, and we see we have a 1 out of 2 configuration here. 1 out of 2. We have a certain coverage factor. We have the proof test interval. There is a mission time. There's a repair time. There's some other parameters. That's all nice, but what we really want to focus on is this beta factor. So let's look at beta, and let's look at the average probability of failure on demand. If I set the beta factor to 0, we will see that the probability of failure on demand is 7.5 E minus 5. So it's a very low average probability of failure on demand. If we would go to, let's say, 10%, in other words, 10% of all failures will result in a common cause event, we see that our probability of failure increases to 7 times 10 to minus 4. So PFD goes up as common cause goes up, and we can see the same, from if we go from 0 to 2%, we see it increase. If we go to 5%, we see it increase, and if we go to the 10%, there's another increase. So as PFD increases, probability of failure on demand increases, just as we would expect. Let's go to the 2 out of 2 scenario. Ignore the top parameters. We'll close the navigation pane here and just look at what we see here. We see there's a 2 out of 2 configuration, the same parameters, all the selections are the same, and we're going to focus on the average probability of failure in demand and the common cause factor. So if common cause will start at 0, we have a probability of failure on demand of 1.34 E minus 2. If we go to 10%, we see that it drops to 1.28 E minus 2. It's minimal. There's only a small drop, but it drops because the system behaves more like a non-redundant system. And non-redundant, 1 out of 1, is safer than 2 out of 2, probability of failure on demand-wise. So we see, if we go from 0, so we had 0%, we see that with 2% it drops, with 5% it drops more, and then with 10% we go to the 1.28. It doesn't have as big of an impact as we saw in the 1 out of 2. For 1 out of 2, we went an order of magnitude between no common cause and common cause with 10%. For 2 out of 2, now it's the arguably the second decimal that changes. And we go from 1.34 to 1.28. So it's 0.06 E minus 2 in this case that changes. It's almost no effect, but there is a slight effect. What will be interesting is to look at the mean time to fail spurious in this case. So we have a gigantic number. Let's see, 4,346,341 years if we don't consider common cause. If we do consider common cause, let's say 2%, we see that that drops immediately to 8,000 something years. 5%, it drops further to 3,000 something years, and the 10% it drops even further to 1,651 years. So significant impact of common cause on the mean time to fill spurious. So 282 was designed to protect against spurious failures, and we see that common cause has a significant impact there. So let's go back to the previous SIF, the 102 SIF. Do the exact same thing. Play with common cause, but focus on spurious failures. So let's see what we can do here. We'll start with 0%. The system is a true redundant 102 system. The spurious trip rate is 82 years. If I go to 2%, it's 82, almost 83 years. If I go to 5%, it's 84 years. And if I go to 10%, it's 86 years. So the same behavior here for spurious failures as what we saw for the 282 from a PFDavg perspective. Slightly better, but only, okay, this is the first, or the integer digit, but we go from 83 to 86. It's almost no difference, but there is a slight improvement because the 102 system is behaving more like a non-redundant system, and non-redundant has fewer spurious trips than redundant from a 102 perspective. So that is how this PFDavg works in Excellencia. Back to the slides, because I've used some values, 0, 2, 5, 10%. How do I come up with these values? And what are typical values for beta? And just as a reference, NASA in the space shuttle study used the common cause factor of 11%. So in other words, 11% of all failures would lead to a failure of redundant systems due to single stress. In IEC 61508, Part 6, Annex D, there is a set of tables that will help you determine your common cause factor. And based on the questions or statements asked and your yes or no on those statements, you will get a certain score, and that score relates to a table. And based on that table, you will be able to claim a certain common cause factor. And that common cause factor ranges from 0.5% to 5% for logic solvers, and it ranges from 1% to 10% for field equipment. Having said that, based on the scores that we can achieve for the different statements made, we cannot get a score that is 120 or above. So practically, our common cause failure rate is going to be 2, 5, or 10% per the standard. Now, this is an informative part of the standard. This is not normative, but it's a good way to come up with a common cause factor and at least give you an idea as to what could be the common cause factor that you should consider. So let's look at Excellencia and how we do that in Excellencia. Well, we have a beta estimator. So let's look at the beta estimator in the tool. For every redundant configuration, as soon as I go from, let's say, 101 to anything redundant, in this case it was the 102 scenario, common cause factor is something I can specify, and with that, the hyperlink here, the beta factor estimator is available. And there is a little explanation there as to what it means, but you will see, and I also showed that on the slide. Let's go back to the slide real quick. Right here. You see there's different sections on separation, segregation, diversity, redundancy, and so on. We have these different sections here in the tool, and based on your, does this statement apply for my particular configuration? Yes, no. You will simply make a selection, and then based on your selections, that score will change, and based on the score, a beta factor will be suggested to you based on 61508. And I'm randomly making some selections. Obviously, I encourage you to actually read the statements before making these selections, but you'll see there's quite a number of selections, and it's of course related on the score associated with them, before I jump from the default 10% to a 5% recommendation. Let's make some more selections here. Even much more before I go to 2%. So there's quite some selections that we need to make before we get to a point that we can justify a 2% common cost. So one of the approaches that one could take is just simply leave it at the default 10%. If it works with 10%, perfect, and it's going to work with a lower probability of with a lower common cost factor. Typically, for configurations that are not n out of n, that are not x out of x, 2 out of 2, 3 out of 3, and so on. It probably makes sense to go through the estimator a couple of times for different scenarios and just come up with default beta factors that you want to use on a project. But that estimator is available for all sensor groups. It's available for all fine element groups. When it comes to the logic solvers, let's see, I can't remember if the data sheets show this. Yeah, okay, so let's go to a redundant, generic SIL3 certified PLC. One of the things you will see here is that, let's see if I can get this highlighted. No, doesn't like it. Okay, so so one of the things you will see when you look at a data sheet is that the beta factor is embedded with the logic solver. So for logic solvers, we don't have a beta estimator. It's just simply part of the data table that we have in the tool for that particular logic solver. For sensors and fine elements, you can determine it yourself. If we look at the voting between groups, our default value is 0% because the different groups are really intended to model completely different measurements, for example. So it could be pressure measurement, a temperature measurement. Typically groups that are really independent, so the default is 0. The default for within a group redundancy is 10%. Again, from a modeling perspective, you always try to model in as few as possible groups for your overall SIL verification modeling. All right, so let's go back to slide set. There is a question here. Let's see. So this question we did. So one of the attendees still has a bit of a problem to look at considering beta for 2 to 2, and I know it's counterintuitive, and there's, from a logical point, yes, absolutely, when beta increases, you would expect PFD to go to increase as well, but look at it from a complete system modeling. Beta does have a negative impact on your 2 out of 2 configuration, but it has that negative impact on that portion of the configuration for which it was designed. 2 out of 2 is designed to reduce spurious trips. Adding common costs will negate the benefits of the redundant configuration with regard to spurious trip protection. There's another question here. Yes, this is also very interesting, and there's a statement or question/statement here. one of the organizations active in field failure study, like Excellencia, Syntef, they did a study where they actually suggested that the beta factor that we're using, or that were based on 61508 to 5-10%, that they are too optimistic. That particular study actually suggests that we should consider beta factors along the lines of 15%. So 15%, which will have an even more drastic impact on the effectiveness of any redundant configuration, be it one of the two or two of the two, for the objective for what they were designed. I'm not familiar with the details of that study. One of the things to consider is we're modeling here with beta factors for product failure rates. If you look at field failure data, one of the things that may come into play is also the overall site's capability. So we're using that from we're using the site safety index to account for that, and that could have a impact similar as common cause on your overall performance, but that's just simply accounted for differently. So I'm not intimately familiar with the details of the study. I've seen the results of the study. I just don't know how they came up with these higher beta factors, if that's accounting for site specific issues in addition to product specific issues, or if it's really just product specific issues. It's very interesting to see people arguing for higher beta factors, because usually it's the other way around. As I said, for the standard, from a standard perspective, oops, I wanted to go up to there. The lowest value that 61508 suggests is 1%, but based on the score, one will never get to that 1%. But I have seen people argue for common cause factors less than 1% for field equipment, even though the valves were mounted right next to each other. What are protection measures against common cause? Usually separation, make sure they have less in common, and diversity. Make sure use a switch and a transmitter. Now that may not be practical, but they will probably behave differently when subjected to the same stress. And as I said, I've seen cases where it's the exact same valve, they're mounted next to each other, and people try to argue a common cause factor less than 1%. So it's usually the other way around. Using a higher common cause factor obviously is more conservative for the configurations that are designed to improve safety. But yeah, I can't speak more than that on the 15% that was suggested by that particular study. All right, let's see. So we talked about the beta estimator. One thing I didn't put in the slides, 61508 also has another table that talks about extra multiplying factors for certain redundancy arrangements. So for example, for a 2 out of 3, you wouldn't just simply use beta, you would use 1.5 times beta. And the reason for that is that there are multiple combinations. A and B can fail, A and C, B and C can fail at the same time, or A, B, and C, all three can fail at the same time. So for certain configurations, there's another multiplier. In Excellencia, we've accounted for that in the models. So you really just need to specify the beta factor. But that could actually be a result as why one would get, let's say, 15%, 1.5 times 10 for certain scenarios. I don't know if that's the case, but that's just something that popped in my head. All right, are there any other questions? Feel free to ask questions on the right-hand side of your webinar. There is the ability to ask additional questions. If there are any other questions, then I'd like to thank you for attending this webinar. This is the first session of 2, so we'll be doing a second session this afternoon. So if any of your colleagues is interested, just tell them at 4 p.m. Eastern daylight saving time there's going to be a second session. There's also going to be a recording of this, and that will be made available to you. There's a question here that says, well, 2 out of 3 is designed to protect against both spurious failures and to improve safety. So how does beta affect? Well, in that case, and we can see that from the equations. So let's go back to the equations real quick. If we look at this, we see that for a 2 out of 3, your PFDavg formula is roughly the same as for a 1 out of 2, and your spurious strip is roughly the same as for a 2 out of 2. So in this case, now you can follow the same approach as I did with 1 out of 2 and 2 out of 2, but let's look 1 out of 2 for PFDavg. Now we will see. Oh, let's erase this. We will see a similar equation here, except the divided by 3 is basically removed. So PFD increasing, beta increasing, PFD will decrease because the square term is becoming less dominant, or the common cause term is becoming more dominant. So increasing beta will decrease PFDavg. If we go to the spurious strip rate, which we have here, this formula was roughly the same. There's roughly a 3x difference between the two, and then the same, adding common cause for the 2 out of 3, increasing beta will increase the common cause spurious strip rate, will therefore increase the overall spurious strip rate. So 2 out of 3 basically behaves exactly as we would expect. Beta increasing, PFDavg increase, spurious strip rate will increase. But using the exact same approach that I did for 1 out of 2 and 2 out of 2, you could say the 2 out of 3 behaves exactly as we expect. All right, so good question. Any other questions? If not, then oh, there's one popping up. So there's another question here with regard to the SynTAF study that was done in the 15% beta. Would a detailed site safety index assessment in combination with the beta factor of 10% or whatever percentage we would come up with, would that equate to the same as the 15% beta that SynTAF suggested? To be honest, I don't know. I would have to see. I can see that has a similar impact. So if you do the site safety assessment, I can see that could have a significant impact, and I would have to run the numbers. But that could probably be something similar as a 15% beta. But we'd have to really look at it. All right, so thank you for attending. Recording will be made available to you later. If there are no other questions, then I'm going to mute myself and sign off. Thank you for attending again, and take care. Bye-bye.